Okay, so today's lecture should finish up exam 4 material. The exam will be on Tuesday of next week, and what I need to make sure is Monday evening there are not extended hours at the testing center for the internet students. So if there is an internet student who cannot get the exam done in time between Monday to Tuesday at by 1 p.m., because if you can take it at 1, you should be in the classroom with us, taking it with us. It'll be better for you. I need you to send me an email and let me know. Otherwise, I will set the parameters like normal, but there is not a Monday evening time. So those internet students need to contact me, and we will go from there and see what we can do. And this would be the same for exam 5 as well. I need to know who those students are. So please email me or personal message me on the A&P website. Okay. Any other questions in general about exam 4 of the last recorded info? All right. So I left off on that last lecture with talking about the functional brain systems. So functional systems were the limbic system, which is more the cerebral part of our functional system. And the reticular activating system, or the RAS, is more related to the brain stem. So that's kind of the difference between limbic versus reticular formation, okay? The limbic system was our emotional brain. It surrounds the commissural tracts, or what we would call what's the commissure mean? It's the corpus callosum. So it's where the right hemisphere can now talk to the left hemisphere and vice versa. So, so this is surrounding that area. The limbic system surrounds that, and it includes parts called like the cingulate gyrus. I'm throwing out some names, but they may not make a lot of sense to you yet. But it's essentially this first picture, if I could draw. Okay, this first picture here is talking about the limbic system. This second picture here is talking more about the reticular activating system, okay? So in this first picture, the cingulate, so this right here is our corpus callosum, right? That's the commissural tracts that allow the right hemisphere to talk to the left hemisphere, okay? All of this purpley pinkish stuff around it is part of the limbic system, okay? So all of this, and this guy, and this guy, and this guy, and this guy here is all part of our limbic system, okay? And there's still some debate on, you know, what scientists say for sure this is or that is, but these are the typical ones that everybody includes. And so the cingulate gyrus is this part right here around the corpus callosum. And also we have what's called the parahippocampal gyrus and the hippocampus. Hippocampus was named because, guess what? It looked kind of like a seahorse. So here's your hippocampus. This is your parahippocampus, kind of around it, para like around. So these two areas are where we store memories and where we also form part of our long-term memory. And so keep in mind, this kind of stuff has to do with the emotional part. So have you guys ever had a memory where you smelled something? Maybe it was the cologne of your dad, or the perfume of your mom, or of some significant person in your life, and immediately when you smell it again, it brings you back to that memory. This is kind of what that is taking you to when we talk about the limbic system. You're making associations based on other sensations, but it creates an emotional response. So did you ever watch a movie when you were a kid and you're kind of thinking like, why is that person crying? That's the dumbest thing I've ever heard of. And then you got a little older and you had more life experiences and you see the same dang movie and you're bawling like an idiot. And you're like, why am I crying over this? Why is this making me feel, you know, like my chest is tightening up, and like, why am I emotional about that character dying? I could care less when I was a kid and saw the same dumb movie. That's your limbic system. And remember, when you're a kid, you don't have as many of those associations between the different neurons. You have a more simplistic, or sometimes I like to call it like psycho killer mentality when you're a kid, like little kid, not like, you know, like a 2-year-old is like a psycho. Have you ever seen, like, they don't care if they hurt like something, right? They don't have that emotional response to it. But as an adult, it would bother you if somebody tried to kill something like that. You know what I mean? You guys kind of see what I'm saying? 2-year-olds really are like psychopaths. I'm just saying. Look at how they process and associate things compared to how you do it now at this age and later. And you really will, go like, oh my gosh. But luckily we grow out of that. We have other things. We make more connections in our brain. And I'll bring that up a couple different times. Another area is the amygdaloid. And this is really where we have like our fear center, our emotional fear, but also extreme like happiness and sadness. Okay. So this is memory based on how we emotionally perceived that event. Okay. Also olfactory bulb and tract, right? So you guys are thinking, what does that have to do with this? So this is like the scent thing. So certain odors that then create a certain or elicit a certain emotional response to it. That could be anything from like disgust. You smell like something really disgusting. You're like, oh, that creates an emotional response, right? So, but also it can be a good response like bacon. And you're like, I like bacon. So, and then also there's anterior thalamic nuclei. So that's coming. So here's our thalamus was here, right? And so you have anterior thalamic nuclei in this area. And also remember the mammillary body that's right under the hypothalamus. So all of those areas are associated with the limbic system. So that's why we call it the emotional brain. It's more in the cortex area. It's around the corpus callosum or those commissural tracts. That's what we're talking about. Versus the reticular activating system or reticular formation. This extends through, it says, the central core of the brainstem. So they're showing you all these little arrows on here, and that's not important for you guys per se for like this exam. But essentially, it was showing like the green arrows coming in, if you can see this, or when you're looking at the information later. So they're showing from the eyeball, this is a green arrow coming in. That was sensory input. The red arrows were the motor output. So this was a red arrow right there. And purple is the reticular activating system output to the cerebrum. So we're saying output, but it's going to the rest of the brain. So that's all of these guys right here. The reticular activating system is sending information out to the cerebrum, the cortex of our brain, the thinking part, right? So I'm going to erase those arrows in a second so you can see them better, but I'm just trying to point out what does this have to do with everything. So let me erase those arrows. Come on. Okay, so reticular formation, this is gray matter. It's motory and a sensory component. It regulates, for example, your muscle tone when you're at rest. So when you're sleeping, you still have muscle tone, right? You're not like a bowl full of jelly and melt away in your bed, although it feels like that sometimes when you're really, really tired. But has autonomic motor function. So this is what also keeps you for respiration, blood pressure, heart rate when you're not aware, right? When you're sleeping and stuff. And this works with the medulla and the pons, which we said actually controls those things. So this is helping with some of that, but it's not controlling it. That's the medulla and the pons. The RAS part of it, reticular activating system, which is the part I want you to know about, is having to do, it's the sensory component of the reticular formation. So sensory component means the visual, the auditory, the touch sensation, that is also affecting your mental alertness. So for example, I said on the last set of notes, all the sensory information coming in goes through the RAS. It's keeping your cortex stimulated, which keeps us conscious. So for example, when we turn the volume down, if we want to associate this like a volume control, if we turn the volume down so we don't listen to all of this extra information so that we can go to sleep, for example, so we have a low level going on, RAS is not really paying much attention. It's not that it's not getting some info. You know how some people are really light sleepers? Their RAS is probably turned up just a little bit more than the other person that is like dead to the world, right? So you have like two kids, you have one that's a super light sleeper and one that's like gone, okay? That's like the difference here. And it says it acts as a filter for familiar signals. So 99% of the stimulus is filtered out. So this is like you put your clothes on this morning. You guys weren't thinking about your clothing until I said the word, you have clothing touching your arm. And then all of a sudden your brain went, what? What's going on over there? Oh yeah, My clothes are on. Good thing I'm not naked, right? Okay. So you don't have to pay attention. Sleeve is touching my arm. Sleeve is touching my arm. Sleeve is touching my arm. That is extraneous. Our brain needs to focus on 100 million other things. That is not something important until it becomes important, right? So it allows unusual stimuli to reach consciousness. So for example, if you were sleeping at night, the RAS is turned down. It's not sending a whole bunch of signals. It's kind of dampened everything down. And then your alarm clock goes off in the morning. Or you happen to live near a farm and you hear the rooster next door crowing. So you get a sound, an auditory stimulus that is out of the ordinary, right? This is not your normal thing that was going on when you were sleeping a minute ago. So it then activates the RAS and turns the volume right up and goes, oh, time to wake up. Let's be conscious. Okay? Then you have like the teenager that hears the alarm system and chooses not to get up. That's a different story. Okay? But that's why it says unusual stimuli to reach brings you back to consciousness, if you will. Okay? And then it says sleep centers in the hypothalamus, decreased activity of the RAS system causes a loss of consciousness. So this is where I was talking about, like if somebody gets punched or car accident or, where you get whipped around all of a sudden. So where is the RAS located? We said it has to do with the brainstem area, right? So if you get smacked or a trauma that causes your head to whip around, whether you get punched in the head, the car accident where you have whiplash, a soccer ball to the head, whatever it may be, right? And it hits you just right that it interrupts the RAS from sending a signal to the cortex, what happens? Zip. You lose consciousness. Because the RAS is what's sending the signal to keep you awake. All right? And when the RAS gets turned down, that's what allows you to go to rest, go to sleep, almost unconscious, right? You're kind of out. You're not paying attention anymore. Okay? So, and then if you had something that disrupts the RAS from sending a signal, because you get a torque or a twist on the brainstem area, now you have no signal, thus it interrupted the signal, thus no signal going to cortex, so you go unconscious. And that's what's going on with something like that, with an injury. So that's why it says sleep centers are in the hypothalamus, decreases the activities of the RAS, so it turns the volume down, allowing you to go to sleep. That's a normal phenomenon. Getting knocked in the head, not a normal phenomenon, right? Even if you're a boxer or a soccer star and you choose to hit the ball with your head, I would recommend not to. But anyway, all right, so that was that. And even when you're asleep, again, the RAS is not turned completely off. It's not like an on-off switch. It's just turned so far down that it allows you to get rest, okay? But it's not completely turned off. That's why if you get an auditory stimulus or your kid all of a sudden is looming over you in the middle of the night and breathing next to you and you wake up, you're like, oh my God, right? That's a stimulus. You had breath hitting you in the face or something, right? Okay, so... all right, so what else do I want to say? So the hypothalamus talks to the RAS. It tells it to turn things down, allowing you to sleep. So hypothalamus talks to the RAS. It puts output to the RAS and tells it to calm down. Okay, let's see. Let's talk about brainwave patterns and the EEG. So we have our gentleman there wearing a super fancy hat. And what he's doing is he's having an EEG, which is an electroencephalogram, EEG, which is just an electrical recording of brain waves. So do you think this tells you what a person is thinking? Nope. It's just telling you what areas of the brain are actively sending signals. But it can't tell you, it can't read the person's mind. It can't say, oh, you are thinking about bacon. No, it doesn't know. It just knows what areas are activated and where are you getting more signals or neurons firing at that time. That's all it's doing. But we have found that we can recognize certain patterns or areas that are activated based on what we saw here and what we could record and what we could understand from that. And so it says brain waves are electrical patterns recorded at the surface of the brain. And what is an electrical recording of the heart called, for example? An EKG or an ECG. It's the same thing. Just depends on whether you know it from the German standpoint or the American standpoint. So it's both electrocardiogram, but they have a very hard C sound, so they did ECG we do EKG. It's the same thing for that. So that's recording the electrical activity of the heart, okay, which we talk more about in 228. ECG is the not cardio because cardio is heart, but electroencephalogram of what the brain activity is doing. So let's see, what else do I want to tell you? Brain waves. So this is frequency of waves. So brain waves are frequency of waves, or to you it might look like spikes in these pictures right here, frequency of waves relating to electrical activity in a particular area of the brain. Okay, so we have 4 types of waves that we want to talk about: alpha, beta, theta, and delta. Okay, so they're kind of a little out of order on how this diagram was talking about it. So the first wave there is called a beta wave. The second wave pattern is the alpha wave. The third one is the theta with a TH, and the bottom one is the delta pattern. Okay. So the alpha wave, this second one in here, this is when somebody is calm, relaxed, but awake. So you guys, for the most part, all are doing alpha waves right now. If we had this fancy hat on your head, you guys are awake, you're paying attention, but you're kind of relaxed, right? If the fire alarm went off all of a sudden, you would all of a sudden not be in an alpha pattern, okay, right? Now that I've given you guys literally a heart attack. People at home are like, turn the volume down, what is she doing? So a beta wave would be where you're thinking, you are, your neurons are firing, one is firing and talking to another neuron, which fires and causes another one to fire, and that type of thing. That's what we mean by thinking. That's the mental activity. That's what the beta wave would look like. So when you guys are trying to figure things out during the exam, might be when you are doing a beta wave. Or if you're really concentrating on what I'm talking about right now, you might be more in a beta function than the alpha wave, okay? Now, a theta wave, TH, is common in children, it says, and adults in their early sleep stages, because we're going to talk about sleep stages in a minute. So what this means is normal adults don't have theta waves going on unless they're in the early stages of sleep. But children have a theta wave typically, okay? So kids are not doing any complicated processing, and you're not typically doing complicated processing, mental acuity, when you're first falling asleep. So that's what they mean by this kind of a brainwave pattern here. Notice that the peaks are a little higher. They're not as close together because, again, it's not as many neurons firing and talking to other neurons. And remember, that would be normal for kids because I told you guys a couple lectures back and today, kids don't have that complicated processing pattern. They don't have all of these neurons and interneurons talking to each other yet. That doesn't happen until you're closer in your 20s and end of the 20s. And then after that, now your patterns are getting set and you're going to have more of an adult brain pattern, if you will, okay? Or hopefully you will. So theta waves would be abnormal in an adult that's awake. Does that make sense? So beta waves are, I'm going to put ABN, because N with a circle for me is normal. ABN with a circle would be abnormal if adult and awake. So if you're an adult and you're awake, but you have a theta pattern, that's a problem. Okay. Delta patterns, it says during sleep, unconscious, when the RES, reticular activating system, is depressed. So the delta waves are when you are in deep sleep. Okay, deep sleep, not the initial early stages of sleep, but deep sleep. All right, so the reason why you see, again, you have higher peaks here, like you were with the theta waves, but they're more spread apart, they last longer, and it's because all of your neurons are kind of firing in sync. It's like everybody on, everybody off, everybody on, everybody off. Instead of like one neuron firing to this neuron, firing to that neuron when you're awake and mentally paying attention, this is like on, off, and And that's why you see a bigger wave pattern here, and it lasts longer between the next peak, okay? So which one would most likely indicate brain damage if the person is not in deep sleep? Delta waves, brain damage. Because it's not functioning right, you're not firing right. You are if you're in deep sleep, that's what you should be doing, but not if you are awake and something had happened, okay? What about when you're really concentrating on an exam, you're doing some complicated math, maybe you're in calculus, maybe you're in algebra, you should be in what phase? Beta waves, because that's your mental acuity. That's when you're you're doing complex processing. Because you're awake in alpha and you're awake in beta, but alpha you're relaxed, right? You're relaxed, not a big deal, okay? You're probably really alert. When I yelled at you a second ago about a fire alarm, that would have been beta because you need to be alert and ready to do something, right? What do we got to do? Where do we got to go? There's an emergency. What is she doing? She's a crazy lady, okay? And where do you guys think children fall? So normally they're in theta, right? They should be in theta, okay? And so they're somewhere between the normal adult and brain damage. Just kidding. Okay. Now the next topic, when we're talking about epilepsy, that's talking about seizures, okay? So when you're looking at these patterns in here, a seizure type pattern is going to be like, you know, crazy peaks and it doesn't look like any of the other patterns there. Okay, and there's two different kinds of epilepsy or seizure type patterns. You could have something called focal, like a focal point, one little area, so that's going to be more mild. And you could have something that is more generalized and kind of all over. So the whole brain can be affected by this, or one focal area could get affected by it, or somewhere everywhere in between. Okay, so if we look at I know the word looks like absence, but it's pronounced absence. This is like Leviosa, okay? Absence seizures. It says they were formerly called petit mal. Mal means bad, petit means little. So little bad. This is mild, so this is more like that focal type of seizure that I mentioned, okay? So I'll put under epilepsy, I'll put focal or can be generalized. So you might have this little focal seizure in one little part of the brain, one focal area, okay? And if you have the absence or petit mal is going to be, if it's in children, it usually will disappear by around age 10. So if in kids, it usually, doesn't mean always, but usually disappears by age 10, okay? So if it's present in children, it will disappear usually around age 10. They are typically unaware of their environment, okay? Unaware of environment. They will probably have like a blank expression, almost like they're staring off into the distance and not looking at you and you're trying to get their attention. So like a blank expression. Yeah, 1,000-mile stare kind of thing. They usually will last about 30 seconds or less. So it's not very long, just kind of looks like they're zoning out for a second. If you Google absence seizure, you'll see a couple of videos of like a parent or a clinician that would have recorded a child that looks like they're zoning out and they're having an absence seizure. And you'll see it's over pretty quick. The kid may or may not even know and usually wouldn't know that it even happened. And it's kind of like they pick up where they left off. And so also, it's called stereotypical activity is present. Stereotypical activity That's an A there. What that means is whatever they were doing before the seizure started, they will continue to do it during the seizure. So if, let's say, they were tapping a pencil on the desk and then they go into an absence seizure, they'll continue to tap it while they're staring off in the distance, and then they'll come to and they might continue to tap and be like, pick up where they left off. You know, that's what it's talking about on stereotypical activity. They'll keep doing it while the seizure is going on. Let's see. And how can you tell if your child is having an absence seizure?
Lights are on, but nobody's home.
But that could be a typical of any kid, so you may not be able to tell unless it's probably something happening very frequently and the kid is not aware and you can't get their, you know, you're snapping your fingers and trying to get their attention. But again, it turns on and off so quickly, and if it's very rare and it's not happening very often with that child, you may not know that they had a seizure, right? You might know if it's happening frequently and you're realizing it's happening all the time, and you finally bring them in and somebody maybe hooks them up to an EEG and kind of is taking a look at stuff, and then they see that rapid pattern going on, because you wouldn't know it otherwise. And again, kids could look like they're staring off and they choose to ignore you and everything, and you're like, my kid's having a seizure. Nope, that's a normal kid right there, potentially, right? So that's why I say you can't always tell. For tonic-clonic seizure, which used to be called a grand mal, so mal meaning bad, grand meaning big, so big bad, right? Grand mal seizure. This is the severe form. They lose consciousness. So the kid with the absence seizure didn't lose consciousness, okay? But the tonic-clonic, the grand mal, they've lost consciousness, convulsions. The reason it says could break bones and bite through their tongue, because all of a sudden you are getting tons of signal. Did you remember that pattern that we just saw a second ago? If you're sending information to your brain, firing everything, do you think that you might all of a sudden be activating your skeletal muscles? And if they contract really hard, you know, you could break a bone. You can bite through your tongue. You know how strong your jaw is, right? So, and they're not aware that they're doing this. So this is going to happen. And so they used to tell people, you know, like stick something in their mouth. Not a good idea. One, you could get bit in the process. Two, you could hurt them. If they break that in half, whatever you tried to stick in their mouth, they could swallow and choke on it. So it's better just to make sure that this person is in as safe an environment as you can. So, you know, yeah, they might, yeah, they could break their teeth on something you're sticking in their mouth. So you literally are just making sure that they're safe and they're not going to, you know, bang into something sharp or stabby or something like that. So, but you don't want to hurt yourself in the process of trying to help that person. So the tonic-clonic can last for several minutes. So a few to several. When the person becomes conscious and aware again, they're usually very disoriented. So a little groggy, confused, so they're not really aware of what just happened. They just know, like, what is going on, you know? So, so when the person awakens, they'll feel disoriented. Okay, let's see if I wanted to add anything else to that. So let's see. And so the kids will typically outgrow or disappear by the 10 years on the absence. Let's see. And again, the absence, they're not unconscious, but they are unaware of what's going on. So you can't really interact with them when they're in that zoned out moment, 30 seconds or less. The tonic-clonic, they do lose consciousness. It can last for several minutes. The person, when they awaken, is disoriented. So basically, just protect them from the environment, call 911, that kind of thing. Let's go on to consciousness. So this is what we lack when we are asleep. Haha, that kind of makes sense, right? It includes that there's simultaneous activity of large areas of the cortex. So when you're aware and things are going on, both sides of the cortex, right and left hemisphere, are firing, getting information, sensory information coming in, potential information as output that you're sending out. So that makes sense. Superimposed on other neural activity. So that just means because you're conscious, the reticular activating system is working, right? Because when that is on, it's sending signals, it's keeping you aware and awake. And so that will then affect your posture, your heart rate, your breathing, everything all at the same time. So that's why it's saying simultaneous other neural activity is occurring. That makes sense. Totally interconnected, meaning information coming from many areas of the cortex. So this is kind of hard to study that information, if you will, because we can try to do PET scans and MRIs to map what's happening and what's going on, but it's expensive. And unless you're doing a well-funded research study, do you think somebody's going to hook you up to this just to see what your little brain's thinking about? No. So that's why it says it's kind of hard to study with that. That's all you really need to know about consciousness. Moving on to sleep. So I kind of think all this stuff with the brain is getting more and more fascinating as we're delving into this. So sleep is a state of partial unconsciousness from which one can be aroused by stimulation. And who's stimulating us to wake us up? The RAS, right? So this is controlled by the RAS and the hypothalamus, because we said they kind of communicate with each other, right? Hypothalamus. Okay. Because remember, hypothalamus says, hey, RAS, turn yourself down so I can go to sleep. And then when you get some sort of stimuli to tell you to wake up or become aware of something going on, RAS turns back up and starts talking back with the hypothalamus again, saying, oh, time to get up and get going, time to think about stuff. So that's why it's by both. So what is a state of unconsciousness where you would not be able to be aroused? Not quite. I mean, you shouldn't be. But what about, say, a coma? Right? So you are unconscious. You're not aware of what's going on. And people cannot arouse you from it until you either never come out of it or you might come out of it 10 or 15 years later. And people are amazed by the miraculous wonder of how you came out of that coma. And then some people, if they're not kept on life support, they're not going to be able to be kept alive, right? So that would be a state of unconsciousness where you could not be aroused. Let's talk about types of sleep, and we're going to get into REM now. Not the band, but come on, am I getting that old? All right, so types of sleep defined by the EEG, so two main stages that we're looking at that we can view, and we're going to talk about this picture down here called the hypnogram by what we're doing with types of sleep. So if we talk about REM first, that means rapid eye movement. So NREM is non-rapid eye movement. That's the difference. Those are the two stages we're going to talk about. So if we talk about non-REM first, non-rapid eye movement, this is broken down into 4 additional stages first. So non-REM occurs before REM, okay? Always has to occur before REM, and it must go through all 4 stages in that first 90 minutes is about how long it takes to do that, to cycle through those first 4 stages before you could go into REM sleep, okay? So the 4 stages we're going to talk about with non-REM, so 4 stages. You have to go through all 4. Have to go, I'm just going to abbreviate through with the wrong way of spelling it, through all 4, which takes about 90 minutes to do, okay? And this is before REM, you have to do this, right? So you have to do this before REM sleep. So what I'm saying is if you don't go through these 4 stages of non-REM, you won't go into REM. Okay, so if you went into non-REM, you start the first stage or 2, let's say, but somebody decides to be like a torture person and they wake you up before you can get into REM, and then you try to fall asleep and they wake you up again before you go into REM. If you don't go into REM sleep, it causes problems mentally. Okay, and it is a form of torture that people, do not do this to people. Okay, I'm not telling you to do this, but it is a form of torture that people have done to cause problems and stuff. But let's get away from that, come back to this. All right, so the first sleep cycle will take you through stages 1 and 2. So first sleep cycle, you'll do stages 1 and then 2, okay? And that takes about the first 30 to 45 minutes of that 90 minutes. So that's 30 to 45 minutes. So you're in stage 1 and 2 that first 30 to 45 minutes. Then you can go into stage 3 and 4, okay, are called, 3 is the slow wave, if you will. So slow wave and or deep sleep. Okay, so 3 and 4 is when you're getting into the deeper sleep. You're not in REM yet. This is the first 4 stages of non-REM, okay? So slow wave is what we call our restorative sleep. So slow wave is restorative. So also, if you went into stage 1 and 2 and they wake you up before 3 and 4, you're not going to feel rested. You're not going to get that restorative sleep. Okay? And then nightmares can occur and only occur in stages 3 and 4. So nightmares only occur during deep sleep and it's in non-REM. Okay, not REM. So deep sleep, this is where we get nightmares. Also night terrors, if you've heard of those, that would be in this phase as well. Okay, so nightmares occur in stage 3 and 4. It occurs in deep sleep. Normal dreams are a REM phenomenon. So a normal dream state is when you're in REM, not in non-REM. Non-REM is restorative. It's getting you to deep sleep. Then you're going to go into the REM cycle after non-REM. So that's after about that first 90 minutes. Now you go into REM. That's when the normal dream state is. That's when you actually have dreams, okay? Which is different than nightmares and different than night terrors. Those are different. So normal dreams are a REM phenomenon, but nightmares are a non-REM phenomenon. Dreams and nightmares are 2 totally different types of occurrences, okay? During slow wave sleep or deep sleep, it's sometimes easier to wake somebody up if they were in stage 1 or 2 when they're in the lighter phases of sleep, the initial stages. It might be a little more difficult to wake them up when they're in stage 3 or 4, but you could, I mean, they might be really groggy and out of it when you're trying to do that, but you could wake them up during that phase, okay? The REM sleep or rapid eye movement, okay, this starts after the non-REM cycle, okay, which begins at about what? 90 minutes. So this is after the first 90 minutes. So after that first 90 minutes, which you were in non-REM sleep, then REM is initiated. So after 90 minutes, REM or this is initiated. It's just fascinating. Okay, so after slow wave sleep has been achieved, the EEG would resemble more of the alpha waves of the awake state. That's kind of cool, right? Because we said you're asleep, but this is where you would have, because you're dreaming, you're thinking things. Have you ever gone to bed and you worked through a problem in your dreams? It may have not seemed like it meant the same thing as like an actual like 1-to-1 ratio of, I'm going to talk in front of my class today and do exactly this. Now you might have some freaky weirdo dream that has nothing to do with it, but whatever problem you were trying to work through, you wake up the next day and you're like, problem solved. I am ready to go. I know exactly what I'm going to do. That's what this is talking about. Okay, so you have the alpha wave of the awake state, helps with memory consolidation. So helps with memory consolidation. Okay, and you must get slow wave sleep before REM can happen. That's why you can't go into REM if you are disrupting somebody from that first non-REM cycle, because slow wave sleep is in non-REM, right? So you must get slow wave or that deep sleep, right? Slow wave sleep, stage 3, 4, before REM can happen. Now, when it says helps with memory consolidation, this is where when you guys try to pull an all-nighter before your big exam, you don't remember all that material you've been trying to stuff in your brain. Versus when you've been studying the day or the week before and you get a good night's sleep before you come in, you get memory consolidation. That's why we say, like people will say, sleep on it, and then we'll work on this again tomorrow. Like you get a fresh perspective. It's because during that REM sleep, you were able to filter through those memories and processes that you were doing during the day and making connections and working through those problems, so that way you consolidate it and put it in like your memory bank, if you will, so you can pull it out and draw from it later. Okay, that's what memory consolidation is talking about. So I know we sound like big meanies when your instructors are in front of you telling you, don't do this, study this way, study that way. We're really trying to help you guys. I know it doesn't always seem that way. Also during REM sleep, you have oxygen consumption. It increases even above the awake state. So remember, this is the dream state when you're in rapid eye movement. Okay, not deep sleep. This is rapid eye movement. So you have increased even more so than your awake state. You have normal dreams occur during this sleep. So this is not nightmares. Remember, nightmares occur when? Non-REM. Okay, REM is normal dreams. Eyes rapidly move, thus the term rapid eye movement, or REM, and it's as if you are scanning your environment. So if you watch somebody who is in REM sleep, their eyelids are shut, but their eyes are moving back and forth like they're seeing things, or like watching somebody run across in front of them. They are doing stuff as if they were awake when this is happening, right? Same things your eyeballs would have been doing, but you're going, but I can't see anything because my eyelids are shut. Yeah, but you're seeing stuff, you're doing stuff, right? Skeletal muscles are inhibited, and this is what prevents us from acting out our dreams, so that you don't whack the person sleeping next to you or try to kill him with the butcher knife or something, right? So skeletal muscles are inhibited. So it's like like, have you ever read something where you heard somebody said, like they woke up and they felt like they were paralyzed and they couldn't move? They probably got their eyes open somehow during that moment where they're still in that paralyzed like state where they can't move their muscles, but they were still really asleep. So, so it prevents you from acting out your dreams. What else do I want to tell you about that? But the weird thing is you still have the movement of the eyeballs, right? Okay. And also your diaphragm is skeletal muscle. So you have skeletal muscle moving the eyes, you have skeletal muscle moving the diaphragm. That's still working even though your other skeletal muscles have been inhibited. Weird, right? But that's what REM does. So what would happen if your skeletal muscles were not inhibited, aside from killing your partner next to you potentially? You could fall out of the bed. You could sleepwalk maybe. So sleepwalking, would it be REM or non-REM? Cannot be REM. You're inhibited in REM. So sleepwalking cannot be a REM phenomenon. It means you must be in non-REM. If you're that goes along with nightmares and stuff. Okay? So sleepwalking, night terrors, nightmares, those would all be under non-REM sleep because you're inhibited in REM. Okay? So nightmares are non-REM. You'll exhibit acting out with your skeletal muscle movement. Night terrors, non-REM, you're in very deep sleep during a night terror, so that's where it's really difficult to get somebody up. If they're in a night terror, it's like they're screaming, screaming, screaming. You can't get them aware and realize they're not in they're safe and they're okay. Yes?
So that feeling you get, like, if you're falling and you're like, oh my God, I'm gasping there, is that non-REM?
It's got to be non-REM. Because you do tend to, kind of jump a little bit when that's happening in that. You're not really in a dream state. You're probably in a somewhat euphoric state, I guess. I don't know. It's kind of, but the funny thing is haven't we all experienced that where you thought you're like riding a bike and fell off? And you had that feeling like, I'm falling, I don't want to fall, I get hurt, but you never hurt. You never smack, but you wake up a lot of times. So we don't have time to go into details about that, but it's fascinating. We all know what we're talking about when somebody says that, right? So, but because you come out, you're way, and can't you guys daydream, right? We daydream, that's not REM, that's not non-REM either. You're not in a deep state. You could be daydreaming just because you're letting your mind wander, which by the way would be doing what with your RAS? Must be turning down because you're not mentally paying attention to something, right? So the volume would have been turned down on your RAS if you're letting your mind wander. And have you guys ever driven somewhere and all of a sudden you become aware like, how the did I get here? I don't remember driving here. I hope I did all the stop signs and the red lights because it was like you were on autopilot, right? It was because your RAS got turned down a little bit. That's what happened. You were still aware. You probably made all the stops like you should have. Hopefully you're in a place you recognize and you meant to go there, right? But that's what that is as well. So good questions, good questions. All right. Let's see what else I want to tell you. So let's talk about typical adult cycles because kids are like psychopaths, right? So we're not going to talk about kids. Let's talk about the typical adult cycle. So remember, you have to go back through the 4 non-REM stages in repeating 90-minute periods, give or take. But each REM period, this is what is interesting, each REM period becomes longer. Okay, so each REM, rapid eye movement period, sorry, that's an M, becomes longer. Okay, so the first time you go into REM, it might only last maybe 5 minutes, maybe. Okay. Maybe by the last time in all of your sleep cycles, because hopefully you're getting your 6 to 8 hours of sleep during the night and you're cycling through these 90-minute time periods, bloop, 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 going back and through them. Maybe by the last time it would have been about 50 minutes long by the last REM cycle. REM would have lasted that long. Yes?
So would it be possible for someone to sleep, uninterrupted sleep and not ever reach REM throughout the whole night?
It's probably possible, and that probably would fall into the realm of where somebody is having some sort of a sleep disorder, where for some reason they're not getting into that phase. So that would be where somebody would go in and get things checked. Maybe they have sleep apnea, let's say, and that's not allowing enough proper oxygen, and maybe they're not going through their deep sleep well enough to allow them to get into REM sleep. So that might be something where they feel like they went to sleep. They may or may not realize they weren't well rested, because if they do this all the time, would they realize the difference? Probably not. To them, that seems normal. They think they're rested, and maybe they're not as rested as they could have been if they went through full cycles, right? So that might be a scenario where that happens, and somebody would go into the sleep study and then monitor their brain waves and see, are they actually getting into REM? Why are they not getting into that phase? So I would say yes. But testing wise for our exam in our class, we won't go into those details, but yes. So each REM cycle becomes longer. And what else do I want to tell you about that? So which REM, remember dream state, which REM are you most likely to remember in the greatest detail? The last one, right? You wake up, you're like, oh my gosh, I just had this weirdo dream. And you know how, like, as the day goes on, unless it was a significant dream, it meant something for whatever reason and more important to you, you tend to forget what you even dreamed about during the night, right? But you feel more refreshed and rested, and because you went into the deep sleep of the non-REM cycle. That's the restorative sleep, right? So if we look at this hypnogram here, so an EEG of what the brain is doing. So this would be the awake phase, and you do have brief awakenings during the night, right? Sometimes you guys have realized you turn over and you realize you woke up for a brief time and went right back to sleep. You just turn over and you're out again. Those would be those brief awake moments during the night. So when you first go in, notice that here you first go to sleep, you skip REM, which was the red lines that we're going to look at in a second, and you go right into stage 1. Then it went into stage 2, and how long did it take you to do that? About 30 to 45 minutes you were in stage 1 and 2. Then you get into stage 3 and then into stage 4, and what is happening during this little dash right there, that period of time in stage 4? What kind of sleep? You deep sleep, so it's the restorative sleep. Do you guys see that here the restorative sleep is shorter? And do you notice you didn't have to go into it over here? If you got enough of your restorative sleep in the first cycle or two, you may not go all the way back down into those cycles anymore. Like a full, you don't have to cycle 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 3, 2, 4, 1, whatever number I just said, right? You don't necessarily have to go like that, because then what happened was after you got to stage 4, so now we must be in our 90 minutes, right? We went through all 4 stages. We pop back up and look where we are with the red line. We are in REM, rapid eye movement. And notice that the dash there is kind of short, right? That might be your first time in REM, so maybe it's only 5 minutes long, give or take. Okay? Then they didn't have to go into stage 2. They went right, or stage 1, they went right into stage 2 on the second cycle of sleep. And they went into 3 and 4, and notice 4 didn't have to be as long, so they didn't need as much restorative sleep, but they still went into it. And this time, instead of popping into REM, they kind of cycled back up to stage 3, stage 2. Then they went into REM. They did get a brief awakening. So in REM, you can be awoken. Okay? And then, but it went right back into REM. So maybe you just turned over and went right back into your rapid eye movement dream phase, right? Of what was going on. And then, see how you can bounce back and forth within this? That's all it's trying to show you there. But you will go through that first 1, 2, 3, 4 in about 90 minutes, and you have to go through that before you'd be allowed to get into REM. That's the key there. And then after that, it's kind of whatever your body kind of needs, right? And you'll cycle back and forth, and then eventually see how like the REM cycle got much longer there. It stayed about the same distance there, and then you time to wake up in the morning. So now you're in the awake phase right there. So let's see. Once you're restored, again, you don't have to go all the way into restorative on every cycle. And that's probably where you're still in these 90-minute cycles probably, but you can spend more time in REM and less in the other phases at that point. But the first one is where you have to go through 1, 2, 3, 4 in about 90 minutes before you can start REM. So now we can talk about memory. So memory is storage and retrieval of information, because if you store it but can't retrieve it, do you have a memory of it? No, because you couldn't retrieve it. You don't have the memory of it. If you can't store it in the first place, will you have a memory of it? No. So that's why it's storage and retrieval. You got to have both in order to have a true memory to work off of, right? So you need both. And it's a two-step process. So what we have is short-term memory and long-term memory. Those are the two we're going to talk about here. Okay. So with short-term memory, this is what we call your working memory. And this is where all things start, right? It first has to go through short-term memory. This can last seconds to hours. Okay? It's limited to about 7 to 8 bits of information. You can think of bits or chunks if you want. So 7 to 8 bits of info. So for example, a 7-digit phone number. You can remember 7 numbers in a row in a sequence for a short period of time. If you don't keep thinking about it over and over, you won't stick it in your long-term memory. You're not going to remember those 7 digits later, right? Why do you think commercials repeat the phone number over and over and over again? Because they want you to have it in your longer-term memory and they want you to call them, right? Otherwise, they don't make any money. And then short-term memory is the first step in memory that can be then transferred into long-term memory. So you have to do short-term memory before it can become a long-term memory. So you can't go long-term that becomes short-term. It's got to be short-term first, then it'll become and locked in, if you want to think of it that way, as a long-term memory. And so you have to do short-term memory, change it in a long-term memory event. So short-term memory has to be transferred. So you can think of it as like a transfer, okay, to long-term memory. And in order to do that, it requires an intact hippocampus. So hippocampus, do you guys remember where that was? Part of your limbic system, right? And when we say intact, we mean not damaged, right? We mean requires intact hippocampus. Remember, that is what looks like a seahorse up in the limbic system, okay? For long-term memory, okay, this is in a different part of the brain. So this is partly why you learn it in one area and you have to end up trying to get it stored or locked in or transferred to the long-term area, which is in a different part of the brain. So this is almost an unlimited storage capacity. So almost, unless you're Johnny Mnemonic, right? Almost unlimited Anybody ever see that movie? Storage capacity. Okay. So we can remember things from a decade ago, right? Or longer. Okay. And if we don't retrieve that memory frequently, and we think about it less and less, it will fade away. Okay, that's why we say memory is a combo of storage and retrieval. If you're not retrieving that memory and thinking about it, it fades. But otherwise, you have almost an unlimited storage capacity of putting these memories in your brain. You can remember them for huge, long periods of time as long as you access that memory frequently enough. So you must use the memory or it will be lost. Must use memory or it will be lost. And the info transfer is from the hippocampus to association areas of the cortex. So info transfer from the hippocampus, which is the short-term memory part. So transfer from hippocampus to association area or areas of cortex. Remember when we talked about all those interneurons talking to each other, making a connection to another neuron and another connection from this neuron to that neuron? Maybe you have 3 neurons that transfer the same info to another one when we talked about converging, diverging, all of those types of things. This is what we're talking about. Okay? So the more connections you can make about something, even though they might seem silly when you come up with a mnemonic or some of these other things, the more likely you're going to be able to retrieve it because you have more pathways to that memory. All right? So this is where it's saying factors affecting the transfer. So this is of information of taking a short-term memory and making it into a long-term memory. So we have information like you have to have a heightened emotional state because that causes norepinephrine is part of what's involved in a memory process. So if you're in a heightened emotional state, you're a little stressed, what do you think happens to norepinephrine? It goes up, right? So what do you think happens when we do evals to you guys? You've got a heightened emotional state, you're a little stressed out, you got a little more norepinephrine flowing through your body, right? So it's not a bad thing. A little bit of stress is good for your memory. We utilize that for you guys. Even though you may not like it, we make you do it, right? But too much stress would inhibit you from remembering or being able to do something, okay? So some is good, but too much is not good. So how do we want to write that down? So extreme stress would actually shift the short-term memory into a long-term memory very quickly. A little bit of stress is good, but too much could impede your memory or inhibit it. Or be detrimental. So let's put extreme stress. This would be like post-traumatic stress disorder, PTSD. Okay, so that is like locking it in and they can't get it out of their head, literally. It locked it right into their long-term memory. They're stuck with that for a while. Because how do you not access it when you keep experiencing it over and over and over again? You're locking it in even more, right? So that sucks. Okay, so emotional extreme stress shifts short-term memory right to long-term memory. A little bit of stress is good. That's why we do well under pressure sometimes when we're trying to get things done and we recall things, right? So a little bit of stress, little stress helps memory. But too much would hinder or impede or be detrimental. Impedes memory. Okay. Why do you think video games work so good? Kids remember how to do this, that, and all the combos that they have to do and run from this monster or that monster. It's a little bit of stress, right? And they don't want to die in the game. Okay. Rehearsal. So repetition helps form memories. You know how we Made you guys go over those muscles again and again and again. That's going to help put it in your long-term memory. Okay, but it can't be passive listening to me like want, 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 want. That doesn't help you. That's why we say you got to be active in your learning to put it in your memory. So you guys paying attention to me, making notes as I'm telling you things, that's being active participant versus just listening to me. You can't retrieve it later and you get on the exam and you're like, I know she talked about it, but I don't remember what she said. Okay, so you have to be actively engaged with the rehearsal. Associating new information with old. This is where you're making multiple connections. This is what a mnemonic is. So M-N-E, mnemonics. It's like taking the first letter of things in your list and it correlates to something else, like when you guys are trying to memorize your cranial nerves for the brain eval. You probably used a mnemonic to remember O to blah, blah, blah. I'm not going to go in there. The dirty ones you remember better, right? You make even more associations with that. Okay. So let's see. Woohoo, we're almost done with this stuff. So associating new information with old. I meant to put mnemonics with that one. Sorry. Mnemonics go with associating new info with old. Let's see. And memory transfer requirements. So what do we need to be able to do in order to transfer the memory and then be able to retrieve it later, right? So hippocampus and surrounding temporal lobe. So what are we saying with this one? Memory imbalances. No, we're not there yet. In order to transfer short-term memory to long-term, we have to have these requirements, which are very important. The hippocampus is where our short-term memory first went, right? Hippocampus, you needed that, okay? And that also with the amygdala, also part of your limbic system, right? And the temporal lobe is where the hippocampus is located in the temporal lobe. So this area must be healthy and intact, right? So must be healthy. Otherwise, if you can't stick it in short term, it's not going to get into long term. So if you want a long-term memory event, then we have to have an intact line of communication between the hippocampus, the thalamus, and the prefrontal cortex. So you got to be able to transfer information. You have to have these guys be able to communicate. So it says this takes time for a transfer and consolidation into long-term memory. So you could think of like the thalamus is like the triage center or the relay center, right? You have a lot of sensory information coming in, and if you're creating a sensory event with the memory, right, it can be motor, like a muscle memory, right? But most of what we're talking about is a sensory type memory. And so let's say you saw something, you heard something, you tasted something, you smelled something. So those all have to be intact and communicate between hippocampus, thalamus, and prefrontal cortex, because short-term memory is hippocampal feature, long-term memory is a prefrontal cortex feature. Long-term memory is stored in the cortex, so the time to get from short-term memory to long-term memory is variable with the event and the individual. Okay, so there's variables in how fast this might actually occur, but you have to have those communication areas working. Now, homeostatic imbalance. This is when it says when something's not working the way it's supposed to, these are the things that can occur. So, memory imbalances like amnesia, meaning like I can't remember something, are either stored, it's either like a storage phenomenon problem or a retrieval phenomenon type of problem, okay? So with anterograde amnesia, they can't remember, so they can't store a recent event. Is that short-term or long-term? Short-term issue, okay? So anterograde means they can't remember the here and now. They can't store it because they're not putting it in short-term memory before it can then, so that it won't get to long-term memory. So this is like a storage problem or short-term memory issue for anterograde. Okay. Retrograde means it's loss of past memories. So a past memory means it went where? It was a long-term memory and you can't retrieve it. So this is a retrieval problem. Okay. You can't access that old memory to bring it to the forward to think about it or do something about it. So these are memories that have been there for a long time and you can't remember those past memories. So you could have a long-term memory, and let's see, let's say you had like a stroke. You lose a portion of the cortex where maybe some of that memory was stored. Okay, you might remember short-term things. Somebody comes in, they talk to you, you have this wonderful conversation with them. You leave the room, you come back in. It's like it didn't happen because they couldn't put it into long-term memory. Okay, but you could come in and talk to somebody, and maybe the area that wasn't damaged, so the long-term memory part wasn't damaged, right? So those areas of the brain were intact and okay, and they know how to have a polite conversation. They know how to eat with a fork. They know how to walk. They know how to do things. Because those were all long-term memories. That didn't get stopped, but they can't learn anything new. They're not going to remember your name. Now, if they had a problem or damage in a long-term memory, like, did you guys ever see the new cartoon, what was that called? With Riley and all the feelings? Inside Out, right? You guys should watch that again with this new perspective. Because, you know, what is she doing? She's trying to store her core memories. Those would have been her long-term memories. Right? She had all these different islands and places that she could access, and the lines of communication where it would shoot the memory back and forth. I mean, rewatch the video. You know, make your kids sit and watch with you or something if you don't want to feel like the adult watching a kiddie movie. But it was actually a really fascinating kind of movie if you look at it from the perspective of how the brain actually kind of works. They were putting kind of good information in there. The kids don't care about that. They're just interested in what happens to Riley and her feelings and disgust and fear. And where's fear housed in? The amygdala, right? So this is kind of really cool. Go back and watch the movie. It's fun. All right. So most common form of amnesia is the anterograde amnesia. So they can't access the information kind of thing, right? Or you go back and watch that movie 50 First Dates, right? With Adam Sandler and Drew Barrymore and stuff. That was kind of a fun movie. So she knew she had long-term memories, right? But she couldn't remember anything she had done from one day to the next day. So hers lasted a few, minutes to hours, and then like the clock reset when she'd wake up, right? She wouldn't remember. She didn't even remember her aging. So he had to make a video to show her what happened in all these other years of her life that they had together. And so that's why they call it 50 First Dates. It was like going on the first date over and over and over again and telling her, we had a connection. You're a stranger, psychopath, get away from me, because he knows about her, she doesn't know him. So that is the end of exam 4 material. Yay! All right. And so after that is exam 5 till the end, and that will be all the material that will be on the next exam. Let's see. So do you guys want to just start that next time?
Yeah.
All right. So I will make a note if I record a lecture, either for Thursday because it is, what's that called? Advising day. I will probably make a lecture sometime between Thursday or before Tuesday at some point, but I will put it on the AMP website that I have recorded the lecture. That would be exam 5 material on that recorded lecture. Any questions for exam 4 material? Yes. I do not come and meet me here on Thursday. I might be here recording the lecture, but I won't be having class. And it's fine if you have questions for me. I don't know if I'll have advising appointments or not yet.
I had a question about the residual activity system.
Yes.
So if it's turning down, would that mean that its activity is actually increasing because it's a filter, but the activity is not?
So the question was if the reticular activating system, the RAS, is being turned, sorry, say that part again. I'm repeating it for the internet people.
It's the stimulus is coming in, so is it working harder, actually the RAS turning up in order to make that stimulus leave?
No, because the RAS is what's sending the signal for you to pay attention to it or not. So it's dampening things down. That's why we say it's like turning the volume down so that you don't pay attention to those signals. Otherwise, you wouldn't be able to go to sleep. So the hippocampus tells the RAS, hey, I'm going to turn off the lights. I'm not going to have any extraneous sounds or stimuli. And now you should be able to go to sleep because I'm not trying to stimulate you with other stuff. So sometimes you are so exhausted and tired that you can go to sleep with all that noise, especially if you're a parent, you learn to deal with it, go to sleep when people are making noise, right? And people can train themselves to have short bursts, what do they call them, power naps, right? But basically what you're doing is the RAS is turning it down. It's not working harder. It's not letting things filter through, going to the cortex and telling it, pay attention to this, pay attention to that. So it's not so much the RAS is working harder, it's just not letting all the signals through. It's dampening down. Think of it more that way. Yeah. Any other exam 4 questions? All right. I'll see you guys on Tuesday for the exam. Remember, internet people, email me if for some reason you cannot make the exam time at the testing center because it doesn't have evening hours on Monday evening. I need you to let me know, so make sure you email me. And, oh, I'll give you guys a clicker for you guys. Sorry.